Angular momentum and fixed axis rotations. We are considering a rigid body that is rotating about a fixed axis. Here the fixed axis we have considered is the z axis. About the z axis, the rigid body is rotating. Rigid body means as it rotates, its shape is not changing. Shape of the body remains constant. This rigid body, we can consider it to be made up of a large number of particles. So one such particle is mj. A big rigid body is there. Mj is one of the particles in the rigid body. Like this, large number of particles together constitute the rigid body. So if you look at a particle, mjth particle, as this rigid body is rotating about the z-axis, let us consider one by one. Mjth particle is at a distance rho j. This is rho j. Rho j is the perpendicular distance from the z-axis to the particle mj. So this is the distance and this is rotating about the z-axis. This is the position vector. Rj is the position vector of the jth particle. And the velocity, this is the velocity vector Vj. As the body is rotating, the velocity is constantly changing. The magnitude of Rj remains constant, but its direction keeps on changing. So, rho j is the fixed distance from the axis. The only way vector r can change keeping its magnitude constant is that the velocity should be perpendicular to r. The velocity v is perpendicular to this r. So what happens is, this is rotating in a plane and the velocity vj is rj dot. R dot represents d by dt. So drj by dt is vj, the velocity at this point. We know v equal to r omega. So correspondingly we can write vj is equal to omega into rho j because it is rotating about, this is the radius of rotation. Rho j is the radius of the circular path. Rho j can be written as, it is in the xy plane. Rho j is in the xy plane. It is xj square plus yj square whole raised to half. So in 3 dimension if you write it, it is equivalent to r equal to root of x square plus y square plus ez square. Since this is confined to an xy plane only, we don't have the z component. So for the jth particle, rho j is equal to xj square plus yj square the whole raised to half. Now the angular momentum of the jth particle. This is the jth particle, its angular momentum. Angular momentum is r cross p. So Lj, angular momentum of the jth particle is Rj cross Mj Vj. The component of angular momentum along the axis of rotation. Axis of rotation is z axis. So since this is rotating in a single plane, the angular momentum is about Lz, about z axis. That is Lz. So Lz of the jth particle is mj vj, which is the momentum, cross distance to the z axis. Distance to the z axis is rho j. This is the distance to the z axis. So this is giving you the magnitude of the z component of angular momentum. Substituting that distance as rho j, you get it as mj vj rho j, and vj is omega rho j. Substituting for vj, you can get mj rho j square omega. So this is for the jth particle. The entire rigid body, when you consider, you have to consider all such particles and sum over them. So the total component of angular momentum Lz is equal to sum over j, Lz of j. Substituting for Lz of j, so this is sum over mj rho j square omega. Sum over mj rho j square equal to moment of inertia I. So this will be equal to I omega. So the z component of angular momentum is I omega. This is the case with you are considering each of these particles as discrete. Now you are considering a continuous distribution of matter. So summation when you are considering continuous distribution, summation is replaced by integration. Since these are discrete, we have applied summation. If it is a continuous medium, you will replace summation by integration. So this becomes equal to integral rho square, and instead of mj you will be writing dm, so that when you integrate you will get the total mass. So this is equal to sum over mj rho j square is our moment of inertia, that is moment of inertia is equal to integral rho square dm. Rho square is the distance of the particle to the z axis, that is equal to x square plus y square into dm. We know density is mass by volume. If rho dash is density, density is mass divided by volume. dm by dv is the density. So I can write dm is equal to density rho dash into dv. So instead of dm I am substituting rho dash dv. So moment of inertia I for the continuous distribution of matter is integral x square plus y square rho dash dv. Next we will be discussing some applications of fixed axis rotation.